Hello everyone, this is lecture 29, the very last one. We have finally reached the end. In this lecture, I plan to lay out for you how the different scenarios explains the phenomenology. In particular, our picture not only was explaining the existing phenomenology, but actually anticipated many new phenomenology. Now, I will go in detail about how our picture explains this phenomenology versus how two models have certain features that appear to resemble the observed phenomenology. At the end, I will quickly summarize the essence of nonlinear polymer rheology. But before closing, I really want to indicate that Thiel model is a very simple, elegant treatment of polymer dynamics under deformation. And it does an extremely well job for linear viscoelastic behavior. But when it comes to nonlinear responses, it seems that we have to think in an alternative way.
Okay, so we really actually jump onto the chapter 18, although it's not the final chapter, but I plan to sort of more or less stop at this chapter. There's a bunch of things that I'm not going to follow this particular outlet. Instead, I will, but of course I will cover much of this topic. Instead, I will start this final discussion like a summary, like a review, by really basically contrasting the two parallel universes and take a look at how these two parallel scenarios explains what we have seen. So instead of following the structure of this chapter, for example, where I just one-sidedly commented on Thiel model first and so on and so forth. So I think the beauty of a class teaching is the flexibility is enormous. Like you have the time. That's a variable that's not in a book. The time factor you can stretch and do whatever. So let's get this part started. Really, instead of 18, which you can read some part of the discussion, let's really have this as if this was a summary of our whole course. And the summary was really going to be about the parallel universe. This I admit to my colleagues when I go to meetings. I said there are two parallel universes. Okay. So this allows me to contrast and to show. In fact, I have all the 28 lectures listed here. I can even pinpoint to go to which lecture for what topic. So let's start. I will start. I mean, I see a simple way to get started is, gee, in rheology, what do? Well, you do a few things. A startup shear versus startup extension. So we'll start with the shear. We simplified our story to shear versus extension. And because we can investigate such simple modes, we don't even need a tensor. We don't even need vector. We only need scalar because we know what we're doing. In shear, we know what we're doing. We're moving this upper plate, making a shape change. So this could be visualized as how much you are displacing, or you should be familiar with sometimes we visualize this with this being the speed of the upper surface. Either way, obviously it involves different notions of how to think about shear. So in shear, so I will speak about this separately, shear and extension. I actually realized that if I write this big, I will be in trouble. I will run out of space very quickly. So let me flip a new page. So this is shear, and if you do shear, there are again just a few ways to do it. One is to start up. One is to step strand, stepwise. And we hardly will talk about so-called oscillatory, because oscillatory is interesting only in the large amplitude oscillation limit. It's going to be nonlinear. So, of course, we're talking about parallel universe regarding nonlinear. We're going to focus only on nonlinear polymer rheology. Okay. So we'll go through these items. I'm going to more or less omit this because not only the book said very little, because it doesn't have any additional insights. That's not covered by the first two modes of examination. So with that, let's start with startup. Now I'm going to try to write it small enough so that I can spread and describe everything. Startup. Of course, it's shear because we're under the topic of shear. And you basically ask yourself, what have we seen? What each type of scenario explains. So I will start with, under this topic, first, scaling. At yield, right? Concerning. So there are already two limits to consider. One is so-called Weissenberg number, Ross-Weissenberg number small versus Ross-Weissenberg number large. Let me, of course, remind you what we are looking at experimentally. We're looking at the shear stress as a function of strand or as a function of time. And we observe that there is an overshoot. Okay. And we can call that gamma y if you wish. Or I wish to do that. Oh, sorry. Okay. Right away, there is a scenario of what we do versus the scenario of what the tube model says. Okay, so we have this word is nowadays so notoriously stupid, but let me still use it to catch your attention, called alternative. We have learned there's such a thing called alternative facts. If you don't catch this political joke, right, that's okay. Sounds like you guys don't. Alternative scenario. So, in short, I will just call it AS in the future, in the subsequent discussion, okay? The tube model says this maximum occurred because of over-orientation. I explained in the beginning part of chapter 16. And specifically, we are talking about this being lecture 24. Isn't that nice if I could point out all that? So, so in fact, everyone who look at this you recorded lecture can go to this very last one for someone who is already familiar with the rest of it, and we will give them the roadmap. We will tell them what is discussed, why we are saying what we are saying, by taking you back to the previous lectures that we have gone through. That would be another way of starting the lecture, starting this course, which is this today, and then go all the way backward. So that says nothing about a structure. Really, I don't call it structureless, but basically it's not related to any failure of the entanglement network. Whereas we were still saying that this is perhaps an issue of disentanglement. And an issue of more importantly, the concept of yield. Yield is a word you can use macroscopically, and the molecular origin is disentanglement. Okay, so so the debate could go on because it's hard to have molecular evidence of either, or rather because of this. The disentanglement is next to an impossible thing to describe because it is not something for you to describe statically. It's not a static picture that can tell you have entanglement on. It's whether these junctions are still effective, right? To permit you to undergo this first part of elastic deformation like a rubber does, versus at what point this becomes impossible, which is occurrence of disentanglement. In this region, there's hardly any universal scaling to speak about, but at high rate, there is. So, for example, in this limit, we find this to be scaling with the Weissenberg number or shear rate to the third power. This is covered in lecture 26. What I omitted to say is to indicate for you what the Thue model says. You can actually trivially guess because of the construct of the Thue model of the Ross retraction. Remember, the chain will retract as soon as you reach tau r, which means it will reach tau r by the time tau r amount of time is reached, right? So what? So it's Wi to the first power, okay? Instead of the third power, yeah? So the contrast is quite large. Experiment basically find this 1/3 law to be more or less obeyed, and we don't observe this power law 1. So I was trying to change the title of today's final lecture. In fact, I did. I want to speak about the difficulty, not only with regard to Thue model, but the challenges with even our new idea. And so I will talk about difficulties all the time. So one of the difficulty here is a good determination of tau r may not be trivial experimentally. So, but I would not say with hesitance that this is experimentally found. No experiment showing showing much stronger scaling. And all this issue also depend on how entangled you are. So it's not a final thing, but it's pretty clear to us. Okay. Let me see what else we have. So this is topic 1 under startup. Topic 2 under startup I probably need to turn another page now, is whether you have localized yielding or not. Or I have this title later, or the question of inhomogeneous shear. Remember, this is all under startup. And as far as we see experimentally, this can occur when the rate is high and when you can neglect, or the wall slip problem is accounted for. Okay? And the way it is accounted for is described in this slide. This actually belongs to the question of chapter 19, which we will sort of skip. But this, anyone who would need to know more can go to this paper to see what happens there. But basically, there is like a phase diagram that shows, depending on the rate you applied and depending on the intrinsic nature of your material, whether your B is large or not, over H, you can anticipate what region will be homogeneous, what region will be wall slip dominated. And you have to, remember we talked so many times, you have to apply high enough rate to enter into the bulk nonlinearity or bulk nonlinear response. So you have to go higher in rate. And how high you go depends on the lambda, the B you have, the B over H you have. So this is a phase diagram. So you have slip first, and you may even have a apparent wall slip, and then you enter really bulk. When I say apparent, meaning the shear bending is not resolvable, and it occurs at the surface. Yeah. And then eventually you see it in the bulk. And you can see this line go through at sufficient high rate, it turns homogeneous again, which we also covered very briefly. So, this is the reason I want to mention this, because the whole picture has to have wall slip addressed. I use a simple case where if you have no wall slip, then obviously you can easily achieve high shear in the bulk. Okay, so under this scenario, under the title of inhomogeneous shear, which what can you do? We cannot avoid it because we observed it. What the two scenarios said, right? The alternative scenario, the tube mode, right? And of course, under the alternative scenario, it's this what we call this also, we sometimes call this shear bending. This shear bending is a result of localized yielding. That's such an abstract word, but basically a disentanglement in a localized manner through a horse, in the sense that there is a horse race. And we talked about whether you could avoid shear bending or not, all depending on whether B over H is large or not. We went through all that, and of course, the shear bending is discussed from lecture 13 all the way to 15. There quite a bit of discussion over there. Let me just describe this and this alternative scenario first. There is further to probe the nature of this. There is further experiment to show that this shear banding is metastable. I want to say it's transient in the sense it's not necessarily there if you can avoid a startup shear. And I'm not going to struggle to look for which lecture covered this, because that's discussed basically in chapter 15, actually. This aspect. It is also in chapter 15. Let me double check. It's also in chapter 15 we talked about what tube model says about shear banding. No, it is 15. And we covered it all. We sort of have an understanding that the horse race can take place and some portion of the sample can be sacrificed. Or rather, once these parts disentangle, they communicate with the rest. So the rest never had a condition to disentangle a similar amount. Consequently, so the point is basically a different level of entanglement coexists basically at the same stress. Coexist. So that seems to be what's happening. And of course, you should know that the tube model, this is the fascinating thing, right? The tube model in the beginning, the original Edward tube model had the symptom of stress over rate being non-monotonic. Okay, so this implies that there will be a scenario where you could have two shear rates locked up there. But that's not how we see it. We see it experimentally. So basically, they think that this will lock up two rates locked up as a function. As a function of the applied rate, V over H. And the issue with this scenario, I shouldn't write just for phenomenological, for accuracy. The axis is V over H. So you can have all different values applied nominally, and then they will phase separate into two rates. This scenario, you can see there's no time here. This is in steady state. So this scenario says you must have shear banding. But this rate run experiment showed you can avoid shear banding if you avoid this sharp startup. In fact, yeah, even though it's difficult to avoid, it turns out you can avoid. So that's a pretty strong contrast about the nature of the of the shear bending. So let me use the remaining space to also add and emphasize that under this column of inhomogeneous shear, a very special case is wall slip. You can use a more fancy word. You can call it interfacial yielding, which essentially, as you know, is due to disentanglement. Here, it's easy to localize because the surface already breaks the symmetry. It already had a bias. So the disentanglement of, if you like, tether chain. Well, why do you have tether chain? Because chains are absorbed. So tether chain from the bulk chain, of course. And of course, this is due to force imbalance. As well. So in this scenario, you may have also observed that you have very good stress growth and then dips down, and that's wall slip. And the whole idea is the slip also require. The whole idea is the slip also require you to reach sufficient deformation before and build enough stress before this disentanglement can take place. Well, on the two model side, it is generally a model for bulk, so there's nothing spoken about wall slip. It's designed to address bulk problems. Keep in mind, it's designed to address phenomenon that supposedly does not involve the concept of yielding, right? So that's the thing. Any questions on this? So that's all I can think of. So we had shear bending or discussing lecture 13 to 15, and this portion about the nature of shear bending is discussed in chapter 15. It's not clear which lecture was it, because I didn't label it that way. But in a more recent lecture, of course, prior to chapter 16. This insight we learned from shear apparently allowed us to think about extension. I think the only part that I should add and have not add is in this scenario here. I want to indicate in this low rate case, I want to indicate that the alternative scenario and two model in many ways are incompatible with each other. What I mean by that is the following. For example, can you claim that this overshoot involves both disentanglement and overall orientation? Well, you cannot quite do that, because, and this question was raised for the two model. Is there disentanglement in two model? Of course there isn't, right? Why? In this limit, there is no chain stretching. And therefore, there is no Rawls chain retraction. And therefore, even you want to blame something like chain retraction for disentanglement, you cannot even blame it because it doesn't happen. Okay? So if you somehow think that there is disentanglement, then you cannot draw a conclusion there is over-orientation anymore. Because if you have disentanglement, then you may not claim that the tube is still there. But if the tube is not there, you cannot work out the theory to indicate that you have over-orientation. So it's rather incompatible, the two scenarios, the two frameworks. So that's why I want to indicate this. Now, this is all startup. So now we can go to look at the fact beyond startup, there is a step extension. And that's, of course, is another confusion, right? This is what I keep saying, that many of the features seem to exist in the tube model, and that's why we're comparing. So in this scenario of, let me just first perhaps write down the introduction first. In other words, now in step strand, we have, I have it in my notes. We have basically a language of so-called elastic yielding. I insist that this is a good word, a good phrase. What do we mean? Well, it actually still means disentanglement. How it happens? Well, actually, it was induced. It is associated with induced force imbalance. How do I induce it? Because you terminated shear. And why does that? What does that do? It will basically turn off the intermolecular gripping force. And what's left is only a level of cohesion force. That is fighting with a large amount of retractive force that you already built through a affine-like deformation. So this imbalance will cause the structure to fall apart through this disentanglement, by the path of disentanglement. And then if this thing can occur in a localized manner, then you have disaster. You have non-quiescent relaxation. Right? So, I'm looking at this for you. So the elastic yielding concept is really first discussed in lectures 19. Okay, and 19 and 20. And if I may continue along this thread, then there is also a rested wall slip for the same physics, and that's discussed in lecture 21. So to discuss this more properly, let me just continue so that you can have, I can use this opportunity to show you where things are discussed. To really describe this properly, to describe disentanglement properly, is really for you to describe entanglement properly. And that's discussed in lecture 22. So I see it, so let me just copy, show you that one. Okay. The whole, the same thing, whether this can produce a visible motion all depend on whether this parameter is large or small, okay? So, let's see what else I can say about it. So, and as I keep saying, this is the most remarkable discovery of all, because this was utterly unknown, that something after step strand could break up. Break up only when it's non-uniformly, it will show motion. It will always break up, but if it break up uniformly, it will not show motion, and it's all dictated by this fact, right? Right? We talk about this, all of this. Go back to their lectures, you'll find it. Okay, so, well, what does the Q model say? Right, step strand is an experiment simpler than anything else because you don't have to strand a lot until you have edge fracture. You don't need to reach that point of facing some experimental difficulties. So, well, you know all along what the Q model does. If you look at the stress, upon stress relaxation, it could have a kink. Experimentally, we call this a kink. Theoretically, this kink, according to the Q model, is due to Rawls. Is due to the premise or assumption or foundation of the Q model that it is assumed that Rawls chain retraction does occur. Not only it occurs without any difficulty, no barrier, barrier-free. So that's how the tube model describes what happens in step strand. And if you look at the stress after the chain retraction, what's left contributing to stress is orientation. And then because of its orientation, and then the more you strand it, remember the step strand, it just means you apply certain strand. The more you strand, the more it's oriented. So as this increases, you could eventually have over-orientation. Over-orientation is something I said in here, over-orientation under this limit. Over-orientation leads to a drop in stress. So similarly, what's left to hold the stress due to chain orientation could suffer the same effect of over-orientation, such that the stress at higher applied strain beyond 2.2 could be lower, because this is nothing but the stress at long times. And therefore, it's very surprising. So let me indicate what I come to demonstrate, what I was thinking today when I tried to prepare this part. Well, tube model says there is a Rawls chain retraction. Let's see hypothetically that's what happened. It does have Rawls retraction, free chain retraction. Then it will produce this red line, which is the so-called famous Dwyer-Edwards damping function. And then I can reconstruct and find at long time the stress will behave as this curve for different strands. Okay? If this could ever occur, it would have also proved that there is indeed this concept of over-orientation is correct. But the logic is precisely the reverse. For not only a small subset of experimental data agrees with this scenario, this quantitative data, but also in no experiment that we know, well, I should make this conclusion less strong. When the experimental curves, data fall on top of this red curve from the two model, at least from the system we constructed, it falls onto this curve because there is non-quiescent relaxation. In other words, sample breaks apart. Further, I would wish to conclude any literature data, any, meaning usually prior to our particle tracking velocimetry measurements, I would, since those measurements did not try to observe whether there is a non-quiescent relaxation or not, I claim that any that follow this line, if you repeat those data, it must have had non-quiescent relaxation. In other words, massive amount of elastic yielding to allow the stress to escape. In other words, no system could produce this red line in a quiescent manner. Or, let me rephrase it, any system that would undergo stress relaxation quiescently will not be type B, will not be type A, will be type B. Look how careful I draw it. Type A, the Dwyer-Edwards theory, has a slope of 2, such that when you try to recover stress, it still is non-monotonic. Type B is carefully drawn such that when I multiply this, it will not drop. Okay, so I'm just saying that any system that can relax quiescently would not show this strong strength softening, which we call. And if that's the case, I also inversely prove that such an interpretation would be wrong. So in other words, there are two things that's wrong. The Rawls chain retraction, that may not be true. But I'm saying if that is true, the overchain orientation is still not true because it cannot be found experimentally, a system that will relax quiescently. So I know I'm saying it very convoluted right now, but all I'm trying to say is for you to satisfy Dwyer-Edwards theory, your sample must be non-quiescent. I mentioned only one part of how to achieve strong so-called strength softening. There's another one that I briefly mentioned. That is if you have wall slip. In other words, you thought you imposed a strength of 10. Actually, you only imposed a strength of 1. In that scenario, but you're not observing it. You're only looking at the final results. you never build that much stress. So in that case, you will have a mass as well. So in any case, I think it's utterly clear to me, at least, that the problem is not as simple as we wish it to be true. The system can indeed undergo failure in a way to escape stress or to lower the stress, because you have a force imbalance, which I indicated, and this force balance is again a horse race. Okay, so it's again a horse race, so it can occur. It can occur it will occur in a localized manner when B over H is large enough. Okay, so I think with that, we're done with the shear part. Let's look at the extension. Equally incompatible between the two scenarios. So you have the alternative scenario where basically, let me again list a few items. I will first say something that is truly elemental. What is that? Well, one says, oh, I can compute for steady state. The other says, no steady state. So this difference is very, very, it cut to the bone now. I mean, what more can you do? This probably is the best place to say, oh, we sometimes do need experiment to guide the theory. Would be one way of saying it, because the theory is blind. It doesn't know. If you don't know the experimental world. Okay? So that's one. The second element is with regard to protocol. Well, that you know. That you know. We talked quite a bit. The sentiment extension rheometry versus FSR. We'll say a little more after this. So next, we can really focus on transient response. Because I already made a brief comment about steady state not being there. So there or not, let's look at transient response. Well, the transient response is utterly straightforward, right? You basically have this. If you look at engineering stress. Okay? And I motivated a great deal about the need to use engineering stress, about whether you're losing this entanglement strength or not. Because, well, we're all guided by probing when the elastic response terminates. And the elastic response, according to near hooking, is this. Then you know each strength, and by the way, it's this. If you're familiar with that notation, it's this. And each strand that is effective is monotonic. Okay? So, you can look for a scenario of non-monoticity when this density starts to drop. And that's how we should be looking for. The structure could fall apart because this density, consequently, the density, the area density falls apart. And so why there's a structural failure? Well, it's disentanglement again. Well, that's what we initially inspired to think, building from the insight that we learned from shear phenomenology. There's force imbalance. Okay, so this actually is one way to explain what's going on. I think it's too weak to say there's a horse race because there is always a winner in this case. Because the different elements are connected in series. So once something weakens, there's no way you can help it. Well, you know, in this case, there is a very subtle and confusing point, which I not only remarked in the book, I recently checked, even it's indexed, where I speak about causality reversal. In any case, let's take a look at what the Thiel model says. Well, the Thiel model, because it can envision steady state, okay? Because it can envision steady state, you have no trouble of visualizing this. That there is eventually stress, of course, true stress, that's no longer changing with lambda. And by definition, well, let me not draw it. By definition, it means you have a maximum. Because you are going to divide, the stress by lambda. So there will necessarily be a part that goes as 1 over lambda by definition. Yeah? Yeah? Come on. So you necessarily will have a peak. Okay? Okay? So if you go back to the original paper model, actually, our great scientists, Duane and Edwards, actually, they are not speaking about steady state. Because they are aware that they want to make connection of that model to what they heard that people tell them that your polymer neck. You see how confusing this is. As time goes by, things get mixed. Because in 79, they know that there are people who are reporting things do not reach steady state, it breaks apart. And the interesting thing is that they want to explain how this thing can break apart. And they invoke the consideration criteria. Which tells them in the engineering books, textbooks, which I made comments in polymer physics too, every year almost, except last year probably. one considerably studied this for metals. He found that if you have a maximum, your drawing will not be stable. In other words, necking, non-uniform, inhomogeneous. And therefore, people start to say, oh, if you have a maximum, by this time you should neck, or some point beyond the maximum, you should neck. Why not? So convenient. The causality reversal that I'm going to indicate one more time, I probably only briefly said it throughout the course, is that this dropping of your force, we know why, disentanglement. It is this disentanglement that produced the dropping. Therefore, the dropping is just the effect. It's just the consequence of disentanglement. In other words, when you apply considerate criteria, you are at a continuum level. You are not worrying about a more elementary question, which is what happened to give you the force dropping? Okay? Instead, as soon as you see force dropping, you conclude using this effect, saying that's the cause. Cause of what? Cause of necking and inhomogeneous extension. Flipping that page beyond, now we tend to forget about this claim and start to recall, oh, isn't there a steady state? In other words, that steady state, as I said, necessarily means there will be a maximum in the engineering stress. You see the point? By definition, come on. The stress is flat here, and you are dividing that stress by lambda, so that part must go as 1 over lambda. And let me just recall for you. This is people's data. I plotted in the way they don't wish to plot. The engineering stress will necessarily have a maximum, of course. So shouldn't you invoke considerate criteria and claim that there is necking? So that's what's happening here. Okay, one more point I further wish to explain is once again going back to a different consideration. With this condition, should you have shear, should you have braking? Well, that depends, right? In other words, if you have this plus considerate criteria, you will say, oh, there will be failure. Except that failure is non-structural. You know, even Maxwell model has exactly that feature. And Maxwell model, being a linear model, of course doesn't have structure. So are we claiming that that's the case? The reason there's nothing structural is, again, in this limit, there's no Gauss chain retraction. Yet we know typically this is almost like a regime 2. Sample still fails. So this is all discussed in chapter 11 in some detail, actually. Okay. So, lastly, we have a stepwise extension. Okay. That's, you may use the same word, that will produce elastic yielding or elastic breakup because of induced force imbalance. That leads to disentanglement. And that disentanglement will produce a winner, no matter what, because it's extension. So the sample, so the sample will suffer, will break up. Remember, this is step strand, so it's breaking up in absence of any ongoing deformation. No choice. And this was reported as a prediction, meaning this is a bit surprising because in shear we know non-quiescent shear is difficult to observe unless you build a device to see it. Well, this is not, right? This is something microscopic in front of you and big, and I would apologize if I made a mistake, but meaning if I missed something in the literature, I think prior to our report, it doesn't, the knowledge of such a phenomenon doesn't exist. That after a large enough step strand, you hold it, it will break. Okay? Now, that's this side. What about tube model? Well, there was nothing. Well, actually, it's very curious. Why didn't they do extension? Now, actually, I need to apologize. Do me a favor. You go back to Do Edwards' book. I don't recall they did extension, step extension. There's an extensive amount of discussion on step shear because of the triumph, because of the success between data and model. But in extension, why not? Well, of course, you would not anticipate breakup. Okay? Because this notion doesn't exist. So let me go back to, I'm done. This notion doesn't exist. What I'm trying to say? I'm saying rheology is all about discussing responses to external deformation. Okay? Well, the traditional rheology says, fine, go ahead and do that. And do that. And just don't ask me to deal with inhomogeneity. Okay? Because typically I speak about strand. Strand field typically is prescribed. Of course, if it's inhomogeneous, you cannot prescribe. I mean, How can you create, right? So this speaks about my last point. I actually paused for a second. I was prepared already to tell you that two models said nothing about step extension. But then, if it does, it would not anticipate anything to break. Because that's just against the spirit of rheology. In fact, the spirit of rheology is very much followed using the FSR. They're trying to save the rheology. Nothing break, nothing go inhomogeneous. So, in summary, our whole subject is about response to extensional, to external deformation. Our whole task, or rather, what we come to realize, much of the physics. Should I add nonlinear response? Fine. But basically, this is the whole subject of the book, right, of our course, nonlinear polymer rheology. It's about nonlinear responses. And much of the physics regarding this response is in the transient part of its story. I think it would be inappropriate to use red color here. So let me change to just a. So, you only need to remember two words for this whole book. Transient and inhomogeneous. Okay? In extension, there is no steady state. So don't speak about it. In shear, steady state is just a tiny negligible fraction of the whole physics. So-called shear thinning, we can speak about it. We even covered that part of it by superimposing some step strand or oscillatory shear to learn about the nature of steady state. Only in shear you can achieve steady state, but even that steady state is difficult to achieve, generally speaking, and impossible to achieve for melts, because we don't have a device that is free of meniscus. There's no such a device that's free of this. Anyone who can tell me a scenario that avoids this, let me know, because we are then in business. In the limit, you can manage to have steady state, for example, by preparing a DNA solution. 1%, 99% water. It can be highly entangled. It behaves identical, in my opinion, to that of a melt. In that so soft system, the edge is not a problem. So you do have steady state. And that's where we'll probe the steady state, actually. But much of this we learn, and much of the processing is never about steady state in shear and extension. So, the whole focus should be on the transient and should be on why the nonlinearity occurs. And the nonlinearity occurs mostly because of the structural change. Because if there is no structural change, you have linear response. Okay? So with that, I think we are done. Now we reduce the whole book not only to 1 page, but to 2 words. Of course, you may, if I'm forced, I may add 1 more word. Or I may combine these 2 words and say that everything we speak about is yielding. Okay, 1 word. How about 1 word? Right? Because the transcendent is all about when the yield occurs, when you fail to have a fine deformation anymore. And then you need to answer why you have a fine deformation, and then you can answer why the deformation can go away. And then the rest is about the manner in which it fails. It could fail localized manner, then you have inhomogeneity. See, it's just 1 word. The entire story is 1 word. With that, I think we can close. All right, so what else there is to say? According to this outline, I do wish to make a comment about some attempts to probe the foundation of the tube model. One of the key foundation is the assumption that this finely deformed tube inside leaves a Ross chain that can retract freely. And as a consequence, it retracts no matter what is the degree of deformation. Therefore, there is no linear response because it will always show a different type of stress relaxation, a different level of stress relaxation, depending on the strength, which means there is no linear response. No linear response. Because, it's in chapter 14, yes, exactly, yeah. So, I'm not an expert on this, neutron scattering. I was speculating in the book about what neutron scattering should be done to probe it. Lo and behold, it turns out Yang was carrying out some creative research on this topic. In particular, he recognized that one way of analyzing neutron scattering data was to do it as the people who have done it for colloid, which is to treat the raw data directly, looking at the intensity and breaking down the neutron scattering intensity directly in terms of summations of so-called spherical harmonic functions, so that your analysis will not be model dependent per se. In any case, one can read the technicalities from this paper. What was carried out was stretching a piece of polystyrene by a factor of 1.8 lambda, so nearly twice, but not there yet. So it's below the finite cohesion limit. So when you extend, sample doesn't break. It sits there stationarily. And then he's going to watch whether the chain retraction occurred or not. Either if it occurs, it has certain feature. If it doesn't, it has certain features. So according to the tube model, which is on the lower left here, the peak of this so-called second spherical harmonic will remain at the same place up to tau r before chain retraction. So this is the tube model. GLAMS stands for a paper in Journal of Rheology in 2003 by a number of outstanding authors. And such a latest the latest tube calculation or model can be used to show that that if there is no chain retraction, this peak or valley, if you like, will not change. Worse. Basically, the experimental data is such that this peak did not change. Okay, that's the experiment. And if Rawls chain retraction occurred, the peak would have changed. So this is the peak initially after step strand, and it moved to other values. So, for example, by the time of tau r, it has changed. That's the red line. So in any case, this is a indication of a disagreement, at least between the data. So this is the data from neutron scattering. This is theoretical data according to the tube model. So they don't agree. Okay, so we reached the end of this class. What I want to say is the road ahead of us may still be rather long in terms of discerning which universe is where we live in. What should be clear is whether the insight we have from this alternative scenario could allow us to make progress in other areas of polymer research. Okay, so it's just because this thing is just such a nasty object. Computer simulation has proven to be still difficult, and mostly because this entanglement concept is dynamic. You cannot take a picture and say, oh, I have an entanglement, or I don't have an entanglement. Not at all. And theoretically, some progress has been made. We have a conceptual idea of basically is force imbalance, right? I can add 3 words to this in total. To formulate this remains challenging, to formulate this analytically. So because of that, I think it will be a while before we could really say for sure how or which one we wish to scenario we wish to proceed. So the best way to go ahead, I know what happens, basically went to the play mode. So the best way to ahead is whether the insight can be helpful. When we probe the effect of processing on structure that could affect the property. And so we're moving along and trying precisely to use our insight to learn how we can influence the structure that sits there to be modified so that our property can be improved. So that's where we are. Nothing is set in stone, but I think we have a pretty good idea about what nonlinear polymer rheology is all about, at least according to the available, mostly macroscopic information or macroscopic phenomenology. So with that, I close. All right, so what else there is to say? According to this outline, I do wish to make a comment about some attempts to probe the foundation of the tube model. One of the key foundation is the assumption that this finely deformed tube inside leaves a Rawls chain that can retract freely. And as a consequence, it retracts no matter what is the degree of deformation. Therefore, there is no linear response because it will always show a different type of stress relaxation, a different level of stress relaxation, depending on the strength, which means there is no linear response. No linear response. Because, it's in chapter 14, yes, exactly, yeah. So I'm not an expert on this neutron scattering. I was speculating in the book about what neutron scattering should be done to probe it. Lo and behold, it turns out Yang was carrying out some creative research on this topic. In particular, he recognized that one way of analyzing neutron scattering data was to do it as the people who have done it for colloids, which is to treat the raw data directly, looking at the intensity and breaking down the neutron scattering intensity directly in terms of summations of so-called spherical harmonic functions, so that your analysis will not be model dependent per se. In any case, one can read the technicalities from this paper. What was carried out was stretching a piece of polystyrene by a factor of 1.8 lambda, so nearly twice, but not there yet. So it's below the finite cohesion limit. So when you extend, sample doesn't break. It sits there stationarily. And then he's going to watch whether the chain retraction occurred or not. Either if it occurs, it has certain feature. If it doesn't, it has certain features. So according to the tube model, which is on the lower left here, the peak of this so-called second spherical harmonic will remain at the same place up to tau r before chain retraction. That's correct. You are so right on this point. You are so right on this point. Thank you. Let me absolutely do something about it. Let me move it to here. Yeah, you are so right. So this is the tube model. GLAMS stands for a paper in Journal of Rheology in 2003 by a number of outstanding authors. And the latest tube calculation or model can be used to show that that if there's no chain retraction, this peak or valley, if you like, will not change. So up to tau r, it will not change. But because of chain retraction, beyond tau r, I think I said it in the reverse. I think I said it in reverse. Basically, the experimental data is such that this peak did not change. Okay, that's the experiment. And if Rawls chain retraction occurred, the peak would have changed. So this is the peak initially after step strand, and it moved to other values. Yeah, so sorry about that. So, for example, by the time of tau r, it has changed. That's the red line. So in any case, this is a indication of a disagreement, at least between the data. So this is the data from neutron scattering. This is theoretical data according to the tube model. So they don't agree. Okay, so we reached the end of this class. What I want to say is the road ahead of us may still be rather long in terms of discerning which universe is where we live in. Okay? That's not as clear, but what should be clear is whether the insight we have from this alternative scenario could allow us to make progress in other areas of polymer research. Okay, so it's just because this thing is just such a nasty object. Computer simulation has proven to be still difficult, and mostly because this entanglement concept is dynamic. You cannot take a picture and say, oh, I have an entanglement, or I don't have an entanglement. Not at all. And theoretically, some progress has been made. We have a conceptual idea of basically is force imbalance, right? I can add 3 words to this in total. To formulate this remains challenging, to formulate this analytically. So because of that, I think it will be a while before we could really say for sure how or which one we wish to scenario we wish to proceed. So the best way to go ahead, I know what happens, basically went to the play mode. So the best way to ahead is whether the insight can be helpful. When we probe the effect of processing on structure that could affect the property. And so we are moving along and trying precisely to use our insight to learn how we can influence the structure that sits there to be modified so that our property can be improved. So that's where we are. Nothing is set in stone, but I think we have a pretty good idea about what nonlinear polymer rheology is all about, at least according to the available, mostly macroscopic information or macroscopic phenomenology. So with that, I close.